So, what is the difference between machine learning, deep learning, and random forest, and how is it linked to econometrics? Very simple. We have been doing this machine learning thing in econometrics for decades when we have done maximum likelihood estimation. You have to understand what maximum likelihood estimation does. It runs an algorithm so that a function, maybe an objective function in this case, is run several many times with many iterations, and with so many iterations it optimizes the function to that we actually accept those parameters that minimizes the difference between a predictor and response variable, or basically kind of like similar to minimizing uh, a gradient descent function in this case. That's what maximum likelihood estimation does. It reduces the distance between predictor and response, and until it reaches that point it continues to estimate. In terms of machine learning, that is exactly the same thing, but machine learning is conducted on non-linear systems of equations mostly. Hence, inside the non-linear, in addition to the linear parameter, we have a non-linear parameter, and inside the non-linear coefficient, it is the parameter that we have is itself is an objective function. And what machine learning primarily does is to minimize that objective function, and that objective function can come from many aspects, many types of objective function. We might have a hyperbolic tangent function, or we might customize a function, you know, that econometrics basically does customize the objective function to include more and more variables that can actually capture shocks, or maybe unemployment rate, anything, instead of a regular tangent function. So that's what machine learning is. However, machine learning has a weakness, or in fact, maximum likelihood estimation has the flexibility to go well outweigh machine learning in terms of this weakness. First of First of all, in terms of maximum likelihood estimation or machine learning, in any case, we start with some assumed initial parameters, right? Assumed value of the parameters that we call initialization. And because these values are either assumed, or a better thing to do is to do OLS and find these parameters and take the OLS estimators, OLS estimations, or the estimators for initializing the estimate of MLE. However, as we are initializing based on some assumption, taking some assumed data to initialize, the quality of prediction basically drops. And that's a weakness of machine learning. Whether, on the other hand, maximum likelihood estimation gets over this by taking, improving upon this idea. For example, if we are talking about a Markov switch model for prediction, or for better or worse, if we are talking about nonlinear impulse response function, or what we know as generalized impulse response function, what does it do whenever we are drawing the function here? It estimates the primary, with OLS it estimates the primary residuals or parameters primarily, then it takes on that value into the objective function, and that it estimates, it optimizes that particular function, and then it, in the third stage, it takes on the optimized parameter estimates for initializing a third phase, where it optimizes again, so a beautiful system where the system is actually, instead of assumption, the system is optimizing multiple times, or replicating this process multiple times, and each time it takes on is it it, the data takes in for this optimization is used for initialization. But when you initialize with a perfect optimized estimation, which in machine learning was being used as final results, you get better responses, right? Your prediction and response distance actually drops. And with more and more research, there are specific uh, ranges for random number generation. For example, in between 0.5 and 1, if your random value is located, it ultimately converges, the predictor response converges, so prediction accuracy increases. So kind of like these things. And these initial data that the system is taking to optimize again and again became known as learning, or moreover, the very new deep learning. So machine learning itself. So whereas machine learning was replicating through many times. Well, machine learning was replicating or running iterations or epochs. The more iteration you run, the better it is for you with some initial value. You replicate the same replication. So the one-time replication is one tree. So if you do many replications of these replications, so you take one tree and you replicate over many times, it kinds of increases the quality. So if your initialization happens based on some perfectly estimated results which are already optimized, obviously your prediction increases, even if it is by one decimal, but it increases. So that's what became kind of like deep learning, a better method. Now, random forest is, I have 10,000 data and I'm replicating, kind of like doing deep learning or machine learning. Now, one-time replication of one-time replication, which includes many iterations, is one tree. Now you replicate many times, but you split this 10,000 data into many different bodies. So you take different combinations of data. So you do 8,000, 7,000, 9,000, and basically you cluster samples from the given data, and you try to find all these possible combinations. So randomly you continue to process this randomly. So maybe 10,000 data is iterated 9,000 times, or the samples that are taken from this 10,000 data gives you probable 8,000 combinations or 7,000 combinations, kind of like Bayesian, right? The probability increases here, looks up. So while we talked about one iteration, one tree. As you have many iterations, many trees, that becomes a forest that is basis on random selection of your sample data, or your random selection of your observations, which is a great method, and that's why it increases prediction, because you might have some bad data, you might have some good data, but because you are taking 10,000, 8,000 sampling, clusters of sampling for this 10,000 data. So if one, I repeat, if one maximum likelihood estimation is one tree, if you have, and you do it 9,000 times, you make a forest. One iteration is replicated 9,000 times, you make a forest with different samples. Your bad data is kind of diminished, it vanishes, and you have good prediction. That is random forest, and that's the objective purpose. So ultimately, this computer science terminology, this econometrics terminology, or health science terminology, they are the same thing. They have been applied many times. So there is no magic in computer learning something or computer defeating you in Go game, like active Go or AlphaGo or in chess. Because what the computer is doing when it is defeated with a chess player, the data that is generated, it initializes its iteration based on that data that is generated from his defeat, and it tries to reduce prediction error by removing the wrong steps it has taken, the errors, and the basically reducing the distance between his prediction and his action response and predictor. In some other terms, by reducing his gradient descent. Okay, that's all. More it initializes, more it learns. It's not learning; it's just changing its initial data for optimization. But its initial data is informed now. Thank you.